Welcome back to Saltwater Stories, everyone, where we journey into the most mysterious corners of the blue world.
It's right.
Grab your metaphoric snowshoes, maybe, and your warmest jacket today, because we are setting the scene in the deepest, darkest, and coldest parts of the ocean.
Yeah, it's a world of, crushing pressure, temperatures near freezing, and just total darkness.
It really is an environment that makes our surface world look, well, pretty easygoing.
Absolutely. But it is home to creatures that have mastered extreme survival over millions and millions of years.
And the star of our discussion today is one of those masters, a creature that kind of glides through that abyssal cold like a silent armored diamond.
Mm-hmm. And it's often associated with those complex hidden structures. We love talking about the deep sea coral reefs.
Right. For those of you who follow us, you know how much we love exploring those hidden deep sea coral cities, the tree houses of the deep ocean.
Exactly.
Well, today we're heading back to see one of the toughest residents living in those deep neighborhoods.
And this resident, it sounds like something out of mythology, actually, which is kind of fitting for a creature that spends his whole life dwelling way down in the midnight zone.
Okay, you've got my interest. What is it?
We are talking about the Arctic skate, Amblyraja hyperborea.
The Arctic skate. The name sounds powerful, but I bet the animal itself is even more surprising.
Oh, it really is. See, when you picture a creature living where food is scarce and it's freezing cold, you might imagine something, slow, careful, maybe just nibbling on little things.
Yeah, that makes sense.
You'd be totally wrong.
Oh, okay. Tell me more.
Yeah.
Well, this is the intriguing opener story, the one that really changed how scientists thought about this bottom-dwelling creature. For years, the assumption was basically that deep-sea skates were mostly scavengers.
Right, eating leftovers or maybe tiny worms.
Exactly, or perhaps just the smallest shrimp they could find.
Yeah.
But then, during research surveys up in the Arctic, scientists started pulling up these skates.
Yeah.
And they discovered they were actually these aggressive, powerful, almost shocking hunters. Whoa. Okay, so what was the evidence? What tipped them off?
It was what they found in their stomachs. Researchers recorded cases where Arctic skates, now these things grow up to about 1 meter long, so not tiny.
Okay, about 3-4 feet.
Yeah. They were found in the process of consuming really large, struggling fish, specifically a fish called the glacial eel pout.
Glacial eel pout. Sounds tough itself.
Oh, it is. It's another resilient, kind of slippery fish from the cold depths.
Okay, so here's a fact, the one that should stick with you, the listener, all day long. What was so shocking about it?
In one case, the eel pout that the skate was trying to eat was, get this, 80% of the skate's own total body length.
Like 80. 80.
80%.
Oh.
So if the skate was, say, the length of a baseball bat, the fish it was eating was almost as long as the bat itself.
That's absolutely wild. I mean, imagine trying to eat a sandwich that's almost as tall as you are.
Exactly.
Yeah.
Just mind-boggling. The prey was so big, so enormous, that the skate couldn't just gulp it down.
No way.
It had to ingest it really slowly over a long period. Often they'd find skates with the tail of this massive fish still sticking out of their mouths.
Wow. Okay, that tells us two things right away. One, this Arctic skate is one dedicated, persistent, and obviously successful hunter.
Definitely.
And two, down there in the food-scarce abyss, when you finally catch a big meal, you absolutely do not let it go, no matter how much effort it takes.
That's the key takeaway right at the start. So our mission today really is to explore this deep sea paradox.
Right.
How does this flat gliding animal built for hiding hunt such huge prey? How is it physically, chemically adapted to handle that insane pressure and freezing cold?
Yeah, and we have to spend time on the baby thing.
Yeah.
Why does its baby take up to 3 years? Did you say 3 years? To have?
Yes, potentially 3 years or even more. It's astonishing.
Okay, and then there's the conservation angle. Why its official status might be, well, dangerously wrong.
Exactly. Lots to unpack.
Okay, let's start with the basics then.
Yeah.
What exactly is this creature? You said it belongs to an ancient lineage.
A very ancient and frankly impressive lineage of fish. We're talking about the class Chondrichthyes.
Chondrichthyes. Okay, sounds complicated.
It does, but if you break it down, chondros is Greek for cartilage, and ichthyes just means fish. So the Arctic skate is a cartilage fish.
A cartilage fish. And for those of us without a biology degree, how's that different from, say, a tuna or a cod?
Okay, think about the bones in your own body. They're hard, right? Calcified, rigid.
Yep.
Bony fish like tuna or cod have skeletons made of that same hard stuff, but touch the tip of your nose
Okay.
or the curve of your ear. Feel how it's flexible but still tough.
Yeah.
That's cartilage. And the Arctic skate's entire skeleton is made of that material. No hard bones at all.
Huh. Does having a cartilage skeleton give it any advantages down there in the deep sea?
Oh, absolutely. A few big ones. First, flexibility. Cartilage is lighter and way more flexible than bone. That really helps with their swimming motion, that smooth, kind of graceful gliding they do across the seabed.
Okay, makes sense.
Second, it saves energy. Building and maintaining a bony skeleton takes a lot of metabolic energy, a lot of minerals. Cartilage is, well, metabolically cheaper to produce.
Ah, important when food is scarce and it's cold.
Exactly. It's a major advantage in that kind of environment. And maybe the most impressive thing, this whole ancient family of cartilage, fish sharks, rays, skates, they've been swimming the oceans for over 400 million years.
400 million. Wow. So they were around way before the dinosaurs.
Hundreds of millions of years before. They are true veterans of ocean evolution, just incredible survivors.
So when we look at its fancy scientific name, Amblyraja hyperborea, you said it's like a secret code.
Huh. Yeah, it kind of is. It's actually the perfect scientific name for it. The first part, the genus name, Amblyraja, it's the
Oh.
combo. Ambly comes from Greek, meaning dark or maybe blunt.
Okay, dark or blunt, like its color or its snout, maybe?
Exactly, referring to its dark gray color and the kind of rounded shape of its snout. And then Raja is simply the Latin word for skate.
So dark, blunt, skate. Got it.
Precisely. And the second part, the species name, Hyperborea. That's even cooler, I think.
Hyperborea. Sounds mythical.
It is. It refers to Hyperborea, which in ancient Greek mythology was this legendary frozen land way up north, beyond the north wind.
Oh, wow.
So you put it all together, Amblyraja Hyperborea literally means something like the dark, blunt skate from the mythical frozen north.
That's fantastic. A perfect name for a creature living in the Arctic deep.
It really captures its essence and its extreme habitat.
Okay, let's play Elasmo Branch detective now. You know, sharks, skates, rays, they all look a bit similar, flat and gliding. How do we tell an Arctic skate apart from its famous relatives, like stingrays?
Good question. There are some key differences, and they mostly boil down to three things. The tail, how they defend themselves, and how they have babies.
Okay, tail first. The tail test. We all know stingrays have that scary whip-like tail.
That's clue number one right there. Rays, especially stingrays, typically have a long, thin, whip-like tail, and often it has one or more sharp, venomous stingers used purely for defense.
Right, you don't want to step on one.
Definitely not. The Arctic skate, though, its tail is relatively short, much thicker, kind of fleshy. And here's the crucial part. It has absolutely no stinger. None at all.
So it's completely harmless to humans in that sense.
Completely harmless. It can't sting you.
Okay, so if it doesn't have that stinger for defense, what does it use? If something bigger tries to take a bite, that brings us to the defense difference.
Right. Since they can't rely on venom, skates rely on built-in body armor. Think of it like medieval armor plating.
Okay, like scales.
Sort of, but more pronounced. They're often covered in sharp, stout spines or thorns called dermal denticles. And the Arctic skate is particularly well armored. It has this continuous, really formidable row of like 22 to 32 large, noticeable thorns running right down the middle of its back.
22 to 32. Wow, where do they run?
They start near its neck area, behind the eyes, and go all the way down its back onto the base of that thick tail.
That sounds like wearing a leather jacket just covered in metal spikes.
It's a great analogy. That armor provides a huge deterrent to potential predators down there, like maybe big sleeper sharks or other large fish.
How does it work? Does it actively use them?
Not really actively. When a threat approaches, the skate just flattens itself onto the seabed, presses down hard. All that's left exposed is that tough, spiny ridge along its back. It makes it a very difficult, very unpleasant potential meal.
Smart. Okay, tail, defense. What's the third clue? The baby clue. You said this is the biggest difference.
This is the absolute defining feature, the one scientists rely on globally. It's about how they reproduce. States are oviparous.
Oviparous, meaning?
Meaning they lay eggs. These eggs develop outside the mother's body, protected inside a special case.
Okay. And rays.
Rays are the opposite. They are viviparous.
Viviparous, like mammals, live birth.
Exactly. They give birth to live young that are fully formed, little mini rays, ready to swim off immediately.
So egg layers versus live bears, that's a huge difference.
It's the fundamental split. So if you ever find one of those tough black or brown, leathery, rectangular pouches washed up on the beach, people often call them mermaid's purses.
I've seen those.
You know, without a doubt, that came from a skate, not a ray.
Okay, so we've got an ancient, armored, cartilage fish that lays eggs. Now, let's look at how it's physically built, engineered to handle an environment that would, frankly, kill most other things instantly. It's deep sea survival suit design,
Right. The whole physical design is just optimized for life on the bottom, the benthic zone. Its body forms that classic flattened diamond-shaped disc.
which comes from its fins, right?
Exactly. Its huge pectoral fins are fused seamlessly to the sides of its head and body, creating those wings it uses to glide. And as we said, it can get pretty big, up to about 112 centimeters long. That's nearly 4 feet.
And its coloring. You mentioned it was dark. Perfect camouflage.
Absolutely perfect. The
Oh.
top side, the dorsal side, is usually a uniform dark mouse gray or maybe brownish color.
Blends right in with the mud or rocks.
Makes it practically invisible to prey swimming above it, or maybe predators looking down. But what's really interesting is its belly, the ventral side.
Oh, what about it?
When they're young, the belly is usually plain white. But as they get older, as they mature, they start developing these dark blotches and speckles. Sometimes the belly becomes almost entirely dark or mottled.
Huh. Why the change?
We're not entirely sure why, but it's a key identification marker for researchers. It helps them figure out the age class or maturity of the skates they find.
Okay, interesting. Now, when this flat creature is buried in the mud or just resting flat on the bottom, how does it breathe? Doesn't it just suck in a mouthful of sand or dirt?
Good question. That's where nature provides a brilliant solution, a kind of built-in breathing snorkel.
A snorkel, really?
Basically, yeah. Most fish draw water in through their mouths to pass over their gills, but the Arctic skate has these two small openings called spiracles right on top of its head, just behind its eyes.
Spiracles up there.
So they act just like a snorkel you'd use when swimming. They allow the skate to pull in clean, oxygenated water from the water column above its head, even when its mouth is pressed right down into the muddy seafloor.
Clever. And where does that water go?
It gets channeled directly to its 5 gill slits, which are located on its underside, its belly. It's just a really elegant piece of engineering that ensures it can breathe clean water while staying perfectly hidden.
Amazing. Okay, let's talk about where it lives its address in the ocean. It's classified as bathydemersal. What does that mean?
The phi-demersal just means it lives on the deep bottom, bathy for deep, demersal for bottom dwelling, and its depth range is just huge.
How huge?
We're talking anywhere from about 92 meters down, which is, relatively shallow, still in the twilight zone perhaps, all the way down to over 3,167 meters.
3,000 meters. That's almost 2 miles down. That's deep into the midnight zone, pitch black.
Deep into the abyss. And that massive depth range brings two constant, really tough challenges: extreme, permanent cold and immense crushing pressure.
Let's tackle the cold first. It's not just cold tolerant. You said it's a cold specialist, a stenothermal cryophile.
Exactly. Fancy terms, but what they mean is it can only handle a very narrow range of cold temperatures. It actively prefers water between about -1 degree Celsius and 4 degrees Celsius.
-1, that's below the freezing point of fresh water.
It is. Ocean water freezes at a slightly lower temperature because of the salt, around -1.8 degrees C or so. This skate thrives right near that freezing point. Anything significantly warmer is actually harmful to its metabolism.
Wow. So its eggs can develop in water that's basically 0 degrees Celsius.
Yep, they've shown that its eggs can develop successfully right around 0 degrees C. It is truly built for the cold.
Now, if it's called the Arctic skate, you'd think it only lives in the Arctic, right? Near the North Pole. But you hinted it's found elsewhere.
This is one of the most fascinating things about it, the bipolar mystery, some call it. This Arctic skate isn't just in the North Atlantic and Arctic Ocean. It's also been documented way down south, off Antarctica, off New Zealand, even off South Africa.
Whoa, wait. How is that possible? Arctic and Antarctic. That's opposite ends of the Earth. Could just a few random ones that got lost?
No, not random occurrences. It's a genuine established range. It's not a fluke. The key isn't the geography, North Pole versus South Pole. The key is the habitat.
Ah, so it's a specialist of the deep, cold habitat itself, wherever that habitat exists.
You've got it. Once you get down below maybe 1,000 meters or so, the deep ocean environment becomes remarkably similar all over the globe. It's always cold, always dark, always high pressure.
Doesn't matter if you're off Greenland or off Tasmania, down deep, it's the same kind of world.
Pretty much. And the Arctic skate is a master of that specific deep, cold habitat. It seems to have used the vast, cold, deep ocean connections, maybe deep currents or pathways over millions of years, to colonize suitable spots at both the North and South Poles. Its range is truly circumglobal in the deep sea.
That's incredible. Okay, let's face the other huge challenge, the pressure. You said 3,000 meters.
Yeah.
What's the pressure like down there?
It's immense. At 3,000 meters, you're looking at about 300 times the atmospheric pressure we feel here at the surface.
300 times. What does that even feel like?
Imagine having the weight of like 300 large cars stacked on top of every square inch of your body. That pressure is constantly trying to physically crush and deform everything.
Including the skate's insides, its cells and stuff.
Especially its delicate internal machinery, the proteins and enzymes that are essential for every life process. Pressure wants to literally unfold them, make them the wrong shape so they can't work.
So how does the skate stop itself from being, well, squished internally?
Yeah.
How does it fight back?
It uses an amazing chemical defense, like an internal chemical shield. It relies heavily on a special little molecule called TMAO.
TMAO.
Yeah. Stands for trimethylamine N oxide. It's a natural compound, and scientists call it a piezolyte.
Piezolyte. Piezo means pressure, right? So a pressure chemical.
Exactly. Think of it as the deep sea equivalent of maybe internal scaffolding or like a natural antifreeze, but specifically designed to counteract pressure.
How does it work?
Well, when that huge hydrostatic pressure tries to physically bend or unfold the skate's vital proteins, the TMAO molecules basically step in. They interact with the water molecules surrounding the proteins in a way that stabilizes the protein structure.
Like creating a little protective bubble around them.
That's a good way to think about it. It essentially creates a microscopic protective barrier, preventing the pressure from messing up the shape of those proteins and enzymes. It keeps all the internal biological machinery working correctly despite the crushing force outside.
That sounds like it must take a lot of energy to make and maintain that TMAO.
It absolutely does. And what's really sophisticated is that the skate seems to adjust the concentration.
Adjust it? How?
As it moves deeper into higher pressure zones, say, going from 500 meters down to 2,500 meters, it has to actively produce and keep higher levels of TMAO in its tissues to counteract the increased pressure.
So it's a constant energy cost, a trade-off for living deep.
Precisely. It's a continuous metabolic investment. Shallow water fish don't need nearly as much TMAO, but for the Arctic skate, having the right amount is absolutely essential for survival in that crushing abyss. Without it, its systems would just fail.
Okay, so it's chemically shielded from pressure, armored against predators, and perfectly camouflaged. Now, how does it actually hunt down there in total darkness? Its eyes, you said, are small and probably not much use.
Right, in the perpetual darkness of the abyss, vision is pretty limited, so it relies on its sixth sense, electroreception.
Ah, the Ampuli of Lorenzini. I love these.
So me too. They're incredible.
Yeah.
Like its shark and ray cousins, the skate has this amazing network of small jelly-filled pores scattered mostly around its snout and head area. These are the Ampuli of Lorenzini.
And they're basically like biological detectors for electricity. Like finding hidden treasure, but the treasure is food.
That's a fantastic analogy. These pores are incredibly sensitive. They can detect the minute electrical fields generated by, say, the muscle contractions or even the heartbeat of other animals.
Even tiny ones.
Even tiny electrical fields. So even if a small fish or a shrimp is completely buried under inches of sand or mud,
The skate can still find it.
it can sense the faint electrical leakage coming from that hidden prey's life processes. It doesn't need to see it. It can essentially hear its electricity.
Hear the heartbeat of a hidden crab through the mud. That's a superpower. That makes it a master of the ambush then.
Definitely. Its whole design, the flattened body, the dark camouflage, is perfect for lying in wait on that muddy or sandy bottom. It just lies motionless, maybe partially buried, using its spiracles to breathe clean water.
Waiting.
Just waiting patiently, using its electrosense to scan the surroundings. Until the electrical signature of a potential meal, whether it's a tiny shrimp or that huge eel pout, comes within range,
And then bam.
then the attack is sudden, usually upward, and powerful. It's guided precisely by those electroreceptors, even in zero visibility.
We talked about its massive appetite eating things 80% of its size. It's considered a high-level carnivore, right? Near the top of its local food chain.
Yeah, its trophic level is estimated around 4.3, which is quite high. That puts it up there as a significant predator in its deep sea ecosystem.
So besides those giant eel pouts, what else is typically on the menu? Is it picky?
Not particularly picky, actually. It's classified as an opportunistic generalist predator. So yes, it absolutely tackles big fish when it can. Besides eel pouts, researchers have found things like blue whiting and even herring in their stomachs.
Okay.
But it also eats a lot of benthic invertebrates, creatures living on or in the seabed, things like shrimp, krill, various types of deep-sea worms, maybe some mollusks.
And its teeth must be suited for that, for grabbing slippery fish.
They are. It has multiple rows of relatively small but sharp pointed teeth. They're more of a grasping type than a chewing type, perfect for latching onto large, struggling prey like that eel pout and just holding on tight once the ambush is sprung.
Makes sense for that persistent hunting style.
Yeah.
But you also mentioned earlier it plays a scavenger role, which seems a bit contradictory for such a powerful hunter.
It does seem contradictory, but it highlights its behavioral flexibility, which is key to survival down there. And this directly links the skate's ecology to human activity.
How so?
In areas where deep water fishing, especially trawling, takes place, the Arctic skate quickly learns and adapts. Studies have shown that in these fished areas, it becomes a really significant opportunistic scavenger.
Scavenging what? Stuff that falls from the surface?
Not just that, it specifically targets fisheries discards or offal.
Yeah.
That's the parts of commercially caught fish, the heads, guts, frames that fishing boats process and throw overboard back into the water.
Ah, so it follows the fishing boats, basically, eating the waste.
It seems to be attracted to those areas. The evidence comes from their stomach contents again. Scientists find large volumes of this fish processing waste, sometimes identifiable parts of commercial species that don't even naturally live right there on that specific patch of seabed.
So it's actively seeking out those discards, not just stumbling upon them.
The volume suggests it's an active switch in foraging strategy. Get an easy, high-energy meal without the effort of hunting.
Seems like a good deal for the skate.
It is, in the short term. Easy calories are great in the deep sea, but it's a double-edged sword. This behavior draws the skates into the very areas where fishing gear is being used most heavily.
Which means they're more likely to get accidentally caught themselves.
Exactly. It increases their risk of becoming bycatch, which, as we'll discuss, is a major threat. So this flexibility helps the individual survive day to day, but it might make the overall population more vulnerable to fishing impacts.
Okay, this whole picture of the Arctic skate is one of patience, endurance, and just an incredibly slow pace of life. And nowhere is that more obvious, more dramatic than how it reproduces. We have to talk about the mermaid's purse again.
Right. This is genuinely one of the most incredible biological stories from the deep sea. When the female skate is ready, she doesn't give live birth. She lays her eggs, but they're protected inside these amazing capsules.
The mermaid's purses, what are they actually like?
They're tough, leathery, sort of like a hardened pouch, usually oblong or rectangular, measuring maybe 8 to 12.5 centimeters long, roughly the size of, say, a large chocolate bar or a small wallet.
And they're not just floating around loose down there, are they? You said they get anchored?
Meticulously anchored. Each corner of the purse had a stiff, pointed horn sticking out.
Horns, like little grappling hooks.
Kind of. The female uses these horns to firmly attach the egg case to something stable on the seafloor. Usually rigid structures like the branches of deep-sea corals or maybe sponges or even just rocks.
Why anchor them?
To stop them from being swept away by strong bottom currents. They need to stay put for a very, very long time. And once that purse is laid and securely anchored, the mother skate's job is done. She provides no further care.
Wow. So the baby inside is totally on its own from day one. How does it survive?
It lives entirely off a large internal yolk sac packed inside the case. That yolk provides all of the food, all the nutrients it needs for its entire development period. We call this lecithotrophic.
Lecithotrophic, living off the yolk.
Yep. The tough case itself, made of proteins similar to like keratin in our hair or collagen, provides all the physical protection for the baby during what is presumed to be an astonishingly long wait.
Okay, here it is. The 3-year wait. This is the fact that just blows my mind every time. Why on earth does it take potentially 3 years, or maybe even longer, for that tiny Arctic skate to finally hatch out of its purse?
It seems almost unbelievable, doesn't it? But it all comes down to the basic physics and chemistry of living in the deep, cold abyss.
The cold.
The extreme cold. Down there where the water temperature is hovering just above freezing, maybe 1 degree C or 2 degrees C, everything happens in slow motion. All the chemical reactions that drive life, including embryonic development.
Like cells dividing, organs forming.
Exactly. All those processes, cell division, protein synthesis, building tissues and organs, they are fundamentally incredibly sluggish at those low temperatures. There's just not enough heat energy to make them happen quickly.
Okay, let's put that in perspective again. A chicken egg hatches in, 21 days?
Roughly, yeah.
A human baby takes 9 months.
Mm-hmm.
This Arctic skate embryo, it could be sitting there for 7,095 days or more.
or more. It's a monumental commitment to slow, patient development.
And is the embryo just dormant inside, waiting? Or is it active?
It has to be somewhat active just to survive inside the case. Remember, it needs oxygen. The egg case isn't totally sealed. It has tiny little slits or pores in the walls to allow water exchange.
Ah, so oxygen can get in.
Right, but it doesn't just passively diffuse in fast enough. The little embryo inside actually has to constantly gently move and fan its tail.
It fans its tail inside the purse. Why?
To create a mini current, pulling fresh, oxygenated water through those tiny slits in the case wall and flushing out waste products like carbon dioxide.
Wow. So for 3 years, it's in there, slowly growing, living off its yolk, and constantly fanning its tail just to breathe.
It requires continuous low-level metabolic effort for years just to stay alive inside its protective shell.
3 years. That's like from starting kindergarten until you're finishing second or third grade, all spent inside a single anchored pouch on the bottom of the deep sea. That's incredible.
It really puts our own timescale into perspective, doesn't it?
It really does. So where do the mothers lay these incredibly precious long-term eggs? Do they just drop them anywhere?
No, because the incubation is so long and the embryo is so vulnerable for so long, the mother has to choose the location very carefully. They don't just lay them randomly. Females deposit these purses in very specific, safe locations known as nursery grounds.
Nursery grounds, like what?
A really crucial discovery was made, for example, off the coast of Tasmania. Researchers found extensive deep-sea coral reefs growing on underwater mountains called seamounts.
And the skates were laying their eggs there.
Yes, these seamounted coral gardens were identified as primary nursery grounds for the local skate population, possibly the Arctic skate or a very close relative found there. The egg cases were found attached all over the coral branches.
Why the coral reefs specifically? What makes them good nurseries?
The complex, three-dimensional structure of the coral provides several really key advantages. First, obvious physical protection. The branches shield the egg cases from being bumped or damaged by currents, or maybe even found by bottom-dwelling predators that might try to eat them.
Okay, shelter.
Second, the water flow around these underwater mountains and through the coral structures can be slightly more dynamic than on the flat abyssal plain.
Meaning more oxygen.
Potentially a more consistent supply of fresh oxygenated water flowing past the egg cases, which is vital for those little embryos fanning away inside for years. That structural complexity seems absolutely crucial for the success of this incredibly long incubation strategy.
This whole slow, careful approach to life, few eggs, long development, long life. In fact, that's what biologists call a case-selected life strategy, right?
Exactly. It's a classic case-selected species, like whales or elephants, or us humans, actually. They invest very heavily in the survival of just a small number of offspring.
Low fecundity is the term.
Right. Low fecundity. Females probably lay fewer than 100 eggs per year, maybe significantly fewer, which sounds like a lot. But compare that to an R-selected fish, like a cod, which might release millions of eggs in a single spawning event.
Millions versus maybe dozens, quality over quantity for the skate.
Definitely. But that strategy comes with inherent vulnerabilities. They mature very late in life.
How late?
Well, data from the North Atlantic suggests females don't even reach sexual maturity until they're about 70.5 centimeters long. Given how slowly things grow in the deep sea, that could represent many, many years.
And we don't even know how long they live.
That's a major critical knowledge gap. We simply don't know their maximum lifespan. But based on related deep-sea skate species, they almost certainly live for decades, maybe 28 years, maybe 37 years, maybe even longer. Nobody knows for sure yet.
So low number of babies, they take years to mature, they live a long time. That combination means the population must have very low resilience.
Extremely low resilience. They just cannot bounce back quickly if something bad happens to them.
What does low resilience mean in practice?
It means their population doubling time. The minimum time it takes for the number of individuals in a population to double is estimated to be painfully slow, somewhere between 4.5 and maybe 14 years.
4.5 to 14 years just to double the population.
Yeah. So if a large number of adult skates are suddenly removed from an area, say by a fishing event, that local population might take generations, decades to recover, if it even can recover at all.
Yeah.
And this slow life history, this low resilience, it brings us to a really crucial and frankly quite dangerous contradiction regarding the Arctic skate's actual survival prospects today.
Okay, because despite everything we just discussed, the 3-year eggs, the late maturity, the super slow recovery time, you mentioned earlier that this skate is officially listed as least concern, LC, by the IUCN Red List.
That's right.
Which Basically implies it's doing okay, it's safe, not immediately threatened.
And that status is now being strongly questioned by many scientists working in the deep sea. The current data suggests it might be dangerously misleading, and it really highlights a huge problem in how we assess the conservation status of deep sea species in general.
Why was it listed as least concern in the first place then? What was the thinking?
The least concern status was largely based on an assumption. The assumption was that because it lives so deep and its range is so vast, its deep habitat essentially acted as a natural refuge from most human threats, particularly fishing.
The logic being,
Mm.
humans don't fish that deep, or not everywhere, so the skate must be safe down there.
Exactly. Out of sight, out of mind, and therefore out of danger. But the reality on the water and under it has changed dramatically.
Especially with fishing technology and the expansion of fisheries into deeper waters.
Yeah, precisely. Deepwater fisheries, particularly those using bottom trawls to target commercially valuable species like Greenland halibut or deep-sea redfish or grenadiers, they are now routinely operating right in the core depth range of the Arctic skate, often between, say, 500 and 1,500 meters deep.
Right where the skate lives.
Right where it lives. And consequently, the Arctic skate is frequently caught unintentionally as bycatch in these deep water trawls.
Bycatch the stuff they catch but weren't targeting.
Exactly. Because it's a bottom dweller, lying flat on the seafloor, it's highly susceptible to being scooped up by bottom trawl nets, which drag heavy gear right across the seabed.
And given its incredibly slow reproductive rate, taking up to 14 years just to double the population, even a seemingly moderate level of accidental catch could be devastating over time, couldn't it?
It absolutely could. It doesn't take catching huge numbers every year to cause a significant decline in a population that replaces itself so slowly. You simply can't reverse that decline easily.
And there's another factor that makes this bycatch risk even worse, right? Something about them being homebodies.
Yes, compounding the risk is the fact that tagging studies where scientists attach tags to skates and track their movements have revealed that the Arctic skate shows high site fidelity.
Site fidelity, meaning they stick close to home, they don't migrate long distances.
They are extreme homebodies. The studies show they exhibit very limited horizontal movement. An individual might spend years, maybe its whole life, within a specific fjord or a deep channel or around a particular seamount.
Okay, why is that important for conservation?
It's critically important. It means that a localized threat, like one intensive fishing operation targeting halibut in a specific fjord, or maybe a pollution event in one area, could potentially wipe out almost the entire resident population of Arctic skates in that specific spot.
Because new ones won't just swim in quickly from somewhere else to replace them.
Exactly. Because they have such high site fidelity and don't move far, there wouldn't be a rapid influx of individuals from adjacent areas to replenish the numbers. Recovery in that specific location would depend entirely on that incredibly slow reproduction or maybe agonizingly slow immigration over years or decades, if it happens at all. It makes them extremely vulnerable to localized depletion.
And the threats aren't just limited to fishing bycatch, are they? As humans push into the Arctic and deeper waters more generally, there are new industrial pressures emerging.
That's right. We absolutely have to consider the looming threats from potential deep-sea mining. There's growing international interest in mining mineral resources found on the deep sea floor, things like polymetallic nodules or cobalt-rich crusts.
And where are those resources typically found?
Often, unfortunately, in the very same types of habitats the Arctic skate relies on abyssal plains, the slopes of seamounts sometimes associated with those same deep-sea coral communities.
So mining could directly destroy their foraging grounds.
Direct physical destruction is a major risk. Mining operations would scrape the seafloor, removing habitat entirely. And critically, it could destroy the sensitive coral nursery sites, where the skates anchor their precious 3-year eggs. Wiping out the nurseries wipes out the future generation.
And mining kicks up a lot of sediment too, doesn't it? Like underwater dust storms.
Huge sediment plumes. That's another major impact. The disturbed mud and fine material can drift for miles on deep currents.
What does that do?
It can smother nearby habitats that weren't directly mined, including other coral gardens or sponge grounds the skates might use. And crucially, that fine sediment could potentially clog the tiny respiratory slits in the mermaids' purses, effectively suffocating the developing embryos inside.
Oh, wow. So mining is a double threat, habitat destruction, and potentially suffocating the next generation.
It poses a severe, multifaceted risk to these slow-growing ecosystems and the species within them.
And then there's the overarching threat of climate change. Even that doesn't offer an easy escape for the skate, does it? You mentioned it puts them in a physiological vice.
Yeah, that term physiological vice really captures the horrible dilemma the Arctic skate faces due to ocean warming. Remember, it's a stenothermal cryophile, a narrow-range cold specialist.
It needs that -1 degree C to 4 degrees C water.
Exactly. So as deep water temperatures gradually rise due to climate change, its preferred cold habitat zone shrinks or is forced to shift into even deeper waters.
So it just follows the cold water deeper. Seems like an adaptation.
It tries to, but remember what happens when you go deeper.
Pressure increases massively.
Right. So to escape the temperature stress by going deeper, the skate simultaneously encounters much higher hydrostatic pressure stress. It's caught between a rock and a hard place, or rather, between warming water and crushing pressure.
The vice.
Device. To cope with that increased pressure, it has to burn more metabolic energy, producing even higher concentrations of that protective molecule, TMAO.
Which means less energy for other things.
Exactly. It diverts precious energy away from vital functions like growing, finding food, and especially reproduction. It severely limits its ability to actually cope with and adapt to rapid climate change. It's a lose-lose situation driven by human-caused environmental shifts.
And all this bycatch, the site fidelity, the mining threat, the climate vice, all these threats are operating against a backdrop of, well, us not really knowing enough about this creature. A knowledge gap crisis.
That's perhaps the most frustrating part for scientists and conservation managers. We're facing these clear and growing threats, but we're often flying blind because we lack the most fundamental biological data needed to effectively protect this species.
Like, why is it so hard just to know how old they are?
It comes back to that cartilage skeleton. Bony fish have hard parts like ear stones called otoliths that lay down annual growth rings like tree rings. Scientists can count these rings to determine the fish's age quite accurately.
But skates don't have otoliths.
No hard, calcified structures like that. Scientists can try to age them by looking at growth bands in their vertebrae, which are partially calcified. But it's technically difficult. The bands can be unclear. And validating the results proving one band equals 1 year is notoriously hard for deep-sea species that we can't easily observe over time.
So we don't have a reliable way to measure their growth rate accurately.
Not easily, no.
We don't know their maximum lifespan for sure.
Correct.
We probably don't know their full reproductive output over that lifespan.
Still many unknowns there, too. And another huge gap is understanding population connectivity.
Meaning, are the skates off New Zealand really connected to the ones in the Arctic? Do they mix?
Exactly. Are they one big interconnected population across the globe linked by deep currents over generations? Or are these populations in different ocean basins effectively isolated genetically? We don't fully know.
And without knowing basic facts like age, growth, lifespan, and connectivity,
Yeah.
how can you possibly set effective conservation measures, like safe bycatch limits or designing marine protected areas?
It makes it incredibly difficult. Any management plan becomes largely guesswork. That's why the current least concern status seems so inadequate, given the known life history constraints and the documented increasing threats. There's an urgent need for focused research funding to fill these critical knowledge gaps before it's too late for some populations.
Wow, we have covered so much incredible ground today, haven't we? Exploring this silent, almost ghost-like predator of the deep abyss. Let's just quickly recap some of the most amazing facts we learned about the Arctic skate so you, the listener, can share this story.
Yeah, definitely. We found out its entire skeleton is made of that flexible cartilage, like your nose, a design that's helped its family survive for over 400 million years.
Right. And its incredible appetite taking on prey that's a staggering 80% of its own body length. A real feat of deep-sea persistence.
And don't forget its invisible chemical shield, that molecule TMAO, constantly working inside its cells to stop the immense pressure from squishing its vital proteins.
Plus its built-in snorkel. The spiracles on top of its head, letting it hide buried in the mud, but still breathe clean water from above. Just genius design.
And of course, the fact that just stops everyone in their tracks. Its babies, sealed inside that tough anchored mermaid's purse, taking potentially 3 years, maybe even longer, just to develop and hatch.
3 years, it's the ultimate testament to life lived in the extreme slow lane. Totally reliant on those specific, safe nursery sites like deep-sea coral reefs for protection during that incredibly long childhood.
And yet, this amazing creature, which has clearly survived millions of years of natural environmental change, is now facing these very rapid, very modern threats from our activities.
Yeah, threats like climate change, putting it in that physiological vice, accidental capture in deep-sea fishing gear, and the potential destruction of its habitat and nurseries by industrial mining. All while scientists are still struggling to gather the basic information needed to even understand how to protect it properly.
And that really brings us to the provocative thought we wanted to leave you with today, you, the listener. The Arctic skate is a creature that evolved over vast stretches of time to thrive in a world that's incredibly cold, dark, stable. A world where time itself seems to move more slowly.
Its whole life cycle, taking maybe decades to replace a single lost generation, demands that stability.
So the question is, what responsibility do we, whose industries, whose climate impacts, whose whole world operates at an exponentially faster pace, what responsibility do we have to protect the long, slow, ancient existence of this magnificent, vulnerable animal, especially as our world continues to speed up and change faster than perhaps ever before?
That is an excellent and really important question to ponder. Maybe next time you look out at the ocean, thinking about what lies hidden deep beneath the surface. Thank you so much for joining us for this incredible story from the deep today.
Yeah, thanks everyone. Hope you found the Arctic skate as fascinating as we do. See you next time on Saltwater Stories.